Kia ora. So we're looking at page 60 of the Walkermaths book. Page 60 of this book here, which is 3.14 probability distributions. And I'm just going to introduce you to the normal distribution. So let's look at some characteristics. So the characteristics of the normal distribution are that it's defined by mu and sigma. Mu just means the mean, which is in this case is actually the mean happens to be the median and the mode as well. So it's just the middle of the data. And then standard deviation, and that just means how spread out it is. I just call standard deviation spread outedness. Now, something that's really important about the normal distribution, pretty much you define it by the mean in the middle, and then if you go 3 standard deviations to the right, and then 3 standard deviations to the left of the mean, that covers about 99% of all of the data. Okay? It is a continuous distribution, which means that your random variable can take any value within this range, and it can actually take values beyond that range as well. It's just really unlikely that that happens. So in fact, this is asymptotic, and we'll have a look at that in a second. So I like to remember mass, M-A-S-S, when I'm dealing with the normal distribution. I remember M for it's mostly around the mean, A for it is asymptotic. This is a fancy word that will get you a merit sometimes. It means that there are no limits. It means that this curve goes on for infinity. And S, it is shaped like a bell. It's quite important to understand that that's what the normal distribution looks like to distinguish it from other distributions. And the final S is that it is symmetrical. If you chucked a mirror bang in the middle, it would reflect left and right. So those are the assumptions of a normal distribution, and that will get you a merit in a few exams. And it will, it's definitely worth knowing these things about the distribution. Okay, so what we'll do is let's just get straight into having a look at one. So I've got a normal distribution here. This formula is like super complicated looking, but you don't actually need to know that at all. So do not worry about that. I am really into it personally. So I've got this one that I've modeled here has a mean of 8 and a standard deviation of 2.5. Actually, let's change that. Let's make it a little bit easier to see this next thing I'm going to explain. So see how the mean is 8, so it is centered around 8. And if you go 3 standard deviations to the right, so that would be 2 times 3, which is 6. So it's got to 8 plus 6 is 14. See how that's got most of the data? 8 minus 6, go down to here, 2, and that's where most of the data is. In fact, this is 100% of the data. So all probability, so this is a random variable, and all anything that can happen is within this area. So that area is equal to 1. It's quite important and worth noticing. Let's move on to an example. So if you look at this here, this is a data set from the US, adults aged 18 to 86 in 2007, and it's just showing a distribution of heights in the US. So let's focus in on women. So see how this is actual data. Now actual data, it tends towards some sort of distribution, but it's obviously there's going to be like little tweaks in the data. It never looks perfect. We never really end up getting like a perfect model when we're looking at the actual data. But what we're going to do today is we're going to model the height of women in the US in 2007. And so let's have a look. What are the 2 parameters we need? We need a mean and a standard deviation. So let's build a model for this. So it looks like the mean is 161 centimeters. Let's remember that. And then what we need to do to work out our standard deviation, let's see what the distance is from the middle, 161, and let's go to where about 99% of the data is covered. Maybe over here at about 182. So 161 to 182 is 21. It's 21 centimeters to the right. Let's just check that that works going to the left. So 161, because we want to check if it's symmetrical, right? 161 minus 21 is 140. that's pretty good. Let's go, yeah, I think 21's pretty good. 21's a nice number. So let's go here. I've prepped it over here. So we wanted a mean of 161 and a standard deviation of, we said it was 21 covering 99% of the data. So it's 3 standard deviations, so we'll have to divide that by 3 and we'll get the number 7. Okay, let's have a look at this model. I'm going to make it look a little bit prettier first of all. Let's go down to like maybe 120 and we'll go up to like maybe 200, just so we can get it looking pretty nice. So this here is a model, whereas before this is the actual data from the sample of women they took. We can then make a model. Now, making a model of something is really important, because once you model data, then you can start to utilize that model to make calls about things. So the thing that we're going to be using our models for in this external is working out what proportion of people fall within different ranges. So let's have a look at an example. So maybe I want to know what proportion of people, or what proportion of women in the United States in 2007 are taller than 170 centimeters. Let's do that first. So what I'm going to do, I'm going to set my first number to be 170 centimeters, and then I want to know all people taller than that. So we're going to have to do like maybe, let's say 200. I need to make sure. Okay, so see how now what we've done is we've used our model to color in a certain area of the normal distribution, and we can then work out what proportion of women we expect to be taller than 170 centimeters. So let's look over here. Here's our proportion that came out, and it looks like it's around about 10% of women, or 9.9% of women. So 10% of women in the US are taller than 170 centimeters, and that's probably fairly accurate, to be honest. See how we used a model, whereas if we were looking at this data, it would only be for this sample of women, and we'd do it for that. Whereas when we're using this model, we have tools that we can use. We have this formula here, and we can then use this formula and these tools to start making better estimates rather than just manually counting women in our sample. We can then clarify models and make them better as well. What else did I want to cover? I think that's about it. Let's have a look at the book and we'll just see what sort of stuff I was missing. So we've talked about that it's continuous. We've talked about that it's mostly around the mean. It has no upper and no lower limit. It's asymptotic. It never touches the x-axis. We sort of talked about that. That it's symmetrical. It always takes this shape. Oh yeah, we sort of want to have a look. I'm going to show you some other stuff. Let's have a look at if we decrease the mean. Let's see what happens. So when you decrease the mean, it just shifts it to the left. Increasing the mean is going to shift it to the right. What about standard deviation? Now, something interesting about standard deviation is the area under this curve will always be 1. So when you reduce standard deviation, it's going to become taller as it becomes slimmer, so that area can remain the same at 1, which I think is really quite interesting, really quite cool. Yeah, let's check this out. Oh yeah, wonderful. Wonderful. Okay, anyway, so yeah, that's an introduction to the normal distribution.